All right. Good morning, friends. Time to begin the lecture. I think there are already some questions. Yeah, so as far as the tutorial is concerned, any question? I have posted the tutorial. I suppose many of you have seen it already. Yeah, so some people were asking questions. Go on now. Oh, am I audible? Could somebody confirm?
Yes, sir.
Okay,
Yes,
cool.
sir, you are audible.
Okay, cool. Apparently there are no questions then, looks like. So tutorial 1 has been posted. We'll discuss answers on, discuss probably not the whole thing, maybe some subset of it, and then we'll continue the rest on in the next tutorial session. Let's see what happens. So tutorial session on we decided Thursday is 6:30, right? So Thursday is what, 19th of August? August 19, 18:30. Okay. Okay. One question I wanted to ask you before beginning the technical content of this class is, okay, raise your hand if you think I'm going too fast. Okay, nobody thinks I'm going too fast. That's cool. Raise your hand if you think I am going way too slow. You know everything, whatever we have discussed so far, so you want to see something new. If you think so, raise your hand. Okay, good, good. Awesome. So I'm wondering, last time people were not able to lower their hands. Now I'm wondering, are people able to raise their hands? So raise your hand if you're awake. Wait, what? Okay, okay. Now I can see the raised hands. Okay, maybe okay. Good, good, good. Yeah, cool. So you can lower your hands now. All right. So you can raise your hands, which means. All right. So Isha, you said you had a question.
Yes.
Yes, Isha.
So my question is a follow-up of that tiling question that we did last
Okay.
class. So
Okay.
it's a different claim that I'm trying to prove that like if we have a particular cell which is not to be covered, so can we say that we will have a unique placement of all the tiles like for a given cell, and then how do we prove that unique placement, that there will be a unique placement?
Is that even true? We'll have to think. Does anybody see something? Have an answer to her question?
So like
Is this
we divide it into 4 quadrants, and like some quadrants will be like completely full without any like blank tile, right? So we can easily show that like we'll be able to make those quadrants with different tilings, like the ones that are full.
Okay,
Because
maybe could you post an explicit example of whatever 4 by 4 or 8 by 8, whatever you find is good enough. Just show that okay, you remove the same cell in both cases, but you get two different tilings. I'm not sure. I'll have to think about this.
okay.
Okay. So in fact, let's all discuss this on the discussion forum. Okay, so that reminds me, discussion forum. I promised I'll start a Piazza forum, but the problem is some of you who have a change in the program, their new Kerberos IDs. I'm not sure whether they have been activated or not. Right. So let's wait for that to stabilize, and then we'll worry about Piazza, Great Scope, everything else. Okay. So for at least for this week, just bear with the Teams discussion forum. Okay, Viraj.
So like Piazza, I think we join it on our own. So I think even if you start it now, it should not be a problem with the Kerberos and all, I think.
Are you sure? Because what I thought was it's like we have to sync with Moodle or something.
Sir, you can provide us with the access code and all, and then we can just join it using our Piazza account. So I think
No,
that is how.
the problem is this access code can easily get leaked outside, and then lots of people join from I don't know where,
Okay.
right? So let's see. I'll figure out. I'll figure out. So later, okay. Hopefully in the next week the Piazza forum should be ready. Okay, cool. Yeah, awesome. So this is not required. Cool. So this is where we ended the last lecture, right? So I gave the statement of the strong induction idea. So what does it say? P is a proposition on the set n union 0 non-negative integers such that P of 0 is true. So the zeroth, okay, so P is essentially something that, okay, so something that makes a statement about every non-negative integer, right? And then the statement corresponding to 0 is true. And now suppose we also are able to prove that if all the previous statements are true, all the statements before the nth statement are true, then the nth statement is also true. Right? So if these two conditions hold, then the claim is that Pn is true for all n. Okay. So if you want, you can just try proving this, assuming the usual principle of mathematical induction. Just convince yourself that this is essentially equivalent to the usual principle of mathematical induction. There is nothing new that I'm saying over here. Just that its kind of syntax is a bit different, which enables you to write, which enables, which will typically enable you to write cleaner proofs in some sense, slightly cleaner proofs. Okay, have you raise your hand if you have seen, if you have used strong induction somewhere before to prove some result? Okay, Mehul, where did you use it?
Sir, I used it once in call 100 actually. Our
what?
TA had, sir, I don't remember the exact question, but I remember that our TA had proposed that we should use this and he had taught us this method once. I
Acha,
don't
acha,
remember
acha.
the
So,
question exactly.
cool, cool. Okay, so I can see
Yes,
that
sir.
at least 1/3 of the class has used it somewhere. Okay, good, good. Okay, so as far as the statement itself is concerned, raise your hand if you knew the statement before. Raise your hand if this statement is not new for you. Okay, so there are a lot of people who knew this from before. Fine, fine. So let us take a quick example of a proof which uses this, so that it's kind of clear to hopefully everybody in the class, and then we'll start something new. Good. So the claim. Okay, you can lower your hands now. Yeah. Okay. So the claim we are going to prove is the following. Okay. Claim. Oh, by the way, before we prove this claim, let me also do this. So there is nothing special about n union 0. So I can also say that if P is a proposition on n union 0 such that, let's say, P of m is true, and then for all, okay, so let me just copy it in fact. Let me just copy it and then change it. Right, so let us say more generally, if P is a proposition on whatever and is such that P of m is true, and then for all n in the set of integers which are okay, which is for every n which is greater than m, okay, n greater than m, the following happens. So P of m, P of m plus 1, and so on up to P of n minus 1 implies Pn. So then Pn is true for all n in n union. Okay, for all. Okay, so let me just in fact change this to the set of integers. Why not? So proposition on the set of integers. So P of n is true for all n in Z, n greater than or equal to m. Okay, Darshan? Darshan, your hand is up. Do you have a question? Okay, apparently not. Cool. Fine. So nothing new in this. So what we'll try to prove using this second version of strong induction is the following claim. Okay, so claim. I mean, I think this is most of you might have seen this proof earlier, but let's do it. So claim every integer greater than 1 can be written as a product of primes, right? So observe that if you use the old-fashioned induction, right? So Pn implies Pn plus 1 or Pn minus 1 implies Pn. That's not going to enable you to prove this kind of a claim, right? So, I mean, the base case is fine. What is the base case? Can somebody tell the base case of this? If you were to prove this by induction, what would be the base case?
2.
Yes, 2.
Sorry, Vibhanshu?
As a 1 is equal to 2 to the power 0.
Sorry, I couldn't hear you. N is equal to what?
N is equal to 1.
N is equal to 1. No, but I'm saying every integer that is strictly greater than 1. No?
Then N is equal to 2. 2 can be written as 2 to the power 1.
Exactly. 2 is a prime. Yes. Good. So by induction on N, so always specify your, okay. Okay. So every integer N greater than 1. So let me just make that change. Fine. So by induction on N, make your plan clear, first of all. Right. So then by base case, what is the base case? Base case is N is equal to 2. N is a prime. So 2 is a prime. So 2 is a product of just one prime. Right, so this is done. Induction case, so inductive case. Right, so assume that you are trying to use the very basic induction statement. What would you assume? So induction hypothesis would be assume Pn minus 1 is true, right? So assume n minus 1 can be written as a product of primes. But now what? Right? So how can you at all use this statement to prove that even n can be written as a product of primes? Not clear. I mean, it will look weird. You can kind of manipulate and maybe do that, but it's not definitely not going to give you a clean proof. Right? So what is the way out of this? We'll use strong induction. Right? So prove by strong induction on it. Right? So in this case, what would be your inductive hypothesis? So inductive hypothesis. So inductive hypothesis is every integer from 2 to n minus 1 can be written as a product of primes. Okay, I forgot to ask something. Okay, raise your hand if you have seen this proof earlier. Oh, I'm surprised. Not many people have seen this earlier. Oh, okay, fine. So apparently there is some delay between you raising your hands and me being able to see this. Fine. Yeah.
Sir, I want to ask, can this claim even be proved? So, I mean, does not this come automatically from the definition of prime numbers?
Sorry?
Sir, means we define prime and we define that a number has to be prime or composite, and every number which is divisible by a certain prime number is a composite. while a number that is not divisible by any prime number, any other prime
Well,
number is a
so
prime. So
acha,
if there
acha,
exists a
acha.
number,
So there is
then
there is slight. I know, I understand. So there is a slight error in what you just said. So any number, what is the definition of a prime? Any number that is not divisible by some other number between 2 and which
the
is less
number
than that
itself.
itself, that is a
Yes.
prime.
Yes, sir.
And anything other than 1 which is not a prime is a composite number. That is the definition of a composite number. That's all.
Yes, sir.
Okay. So then what is your argument? So why does it imply that the composite number is divisible by some prime number? Not clear, right? Immediately we'll have to prove
Sir,
it.
no, sir. It implies composite number is divisible by prime number, as if it would not be divisible by any prime number less than the number itself, then it would be a prime. Because
That's not
we
the definition
define.
of being a prime, no? I mean, what you're saying is correct, but that's not a proof. That's not the definition of being a prime.
No, sir. Sir, listen. Sir, we define prime number as a number which is not divisible by any number between 1 and the number itself. Yes?
Correct, correct, correct. Any number, huh?
So,
Okay.
yeah, any number. So I want to ask for a composite number. If a composite number is divisible by some number between 1 and the number itself, then we have something left to do. Otherwise, it would be a prime if it is not divisible by some.
Correct. So that's what we are going to do now. So if the number is prime, then the claim is obvious. If the number is
okay,
composite,
sir,
then
okay, sir, I got it.
Okay, good. So this is the induction hypothesis, and then how do you prove the claim? So if right, so proof by cases. This is something we did last time. So proof by cases. If if n is a prime, then it is a product of 1 prime. Right, so this is what we wanted to prove. Fine. Else, right, so n is composite. Right, so by definition, there exist integers. Let's say m1, m2, m1 and m2, such that what? N is composite, no? So n is equal to m1, m2, and right. So this is a non-trivial factorization. So and what? 1 is strictly less than m1, and which is strictly less than n. 1 is strictly less than m2, strictly less than n. Dhruv? Yes, Dhruv, what is your question?
Sorry, sir, I forgot to lower my hand.
Okay, fine. Okay, so then what? Now we'll use our strong induction hypothesis, right? What is our strong induction hypothesis? Every induction from 2 to n minus 1 can be written as a product of primes, right? So m1 is an integer between 2 and n minus 1. m2 is also an integer between 2 and n minus 1. So therefore, by induction hypothesis, both m1 and m2 can be written as products of primes, right? So that is what m1 is equal to some p1, p2, blah blah blah, up to some pk, and m2 is equal to q1, q2. Possibly there are repetitions. Possibly some pi is equal to qj, pi is equal to pj. All sorts of things are possible. Up to some ql, where k and l are some natural numbers, and p1 through pk, q1 through ql are primes, right? And therefore n is equal to p1 through pk times q1 through ql, right? So thus n is a product of primes. right? So the technical part of the proof is completely trivial. What I want you to pick up from this proof is how do you write a proof using strong induction? That's all. Samyak?
Sir, I wanted to know how can we say that this will be unique? Like separate question, but how can we say this?
That's not even a claim right now, right? So if
That's a separate
that requires non-trivial amount of number theory, that requires a result which, for example, will say that okay, if the product of two numbers is divisible by a prime, then one of the two numbers is all divisible by that prime. So all this non-trivial number theory will start getting involved if you want to prove the uniqueness, right? But just for the existence of a collection of prime numbers whose product is a given number n, you don't require all such all that stuff. Just strong induction is good enough. Is that fine?
Okay.
Yeah, cool. Yeah, awesome. So now let us write down one more claim and let us see what kind of induction we are able to use to prove that claim. Right. So the claim I want to make is the following. So even before I write down the claim, let's try to understand a specific number that is involved in this claim, right? So I'm looking at this number. I'm looking at the following number, square root of 1 times square root of 2 times square root of 3 times blah blah blah, square root of n, and remember all these are nested square roots, right? So there's something. This is square root of 3 times blah. Right, so I hope this number is clear. Right, so if you were to write it out as a product of powers, what this would be equal to is 1 to the power half times 2 to the power 1/4 times 3 to the power 1/8 times blah blah blah, n to the power what? N to the power what?
1 by 2 raised to power n.
1 by 2. Good. Right. So now as n increases, what happens to this number? Does it increase? Does it decrease? Does it go to infinity? Does it converge somewhere? Any intuition? Does it increase or decrease? Obvious question.
Increase.
Increases.
Increase. Good. So now does it increase to infinity or do you think it will converge somewhere? Sorry?
I think it will convert somewhere.
You think it will convert somewhere? Good. Okay. Is there anybody who thinks it will go to infinity? Okay, nobody. Any guess of what it will converge to? Any upper bound on this? I mean, I'm not looking for an exact limit over here. Just give me an upper bound. Yes. Sorry?
2 is upper bound.
2 is an upper bound. Okay, cool. So who is this? Can you tell your name? I didn't notice who answered.
Hitesh.
Sorry?
Hitesh.
Okay, Hitesh. All right.
Yes.
So the claim seems to be that this is certainly less than 2. Okay, right? So the claim seems to be that this does not go to infinity, and in fact this is less than 2, and this is what we are going to prove now. Okay, so let me just make it into a claim. Right, so for every n.
This claim is wrong.
This claim is wrong. Why?
Yes, sir. For n equal to 4, it comes out wrong.
Really? N equal
Yes,
to 4.
sir.
Let's see. So 1 to the half is just 1. Ignore that. 2 to the 1/4 times 3 to the 1/8 times 4
Sorry,
to
sir.
the
We have 2
1/6.
to the 1/4. Sir, I did square. Okay, fine.
Sorry, what was the confusion?
Sir, actually, I ignored the first square root. I mean, I did under root 2 into.
Oh, got it. Okay, fine. No issues. Right. So, yeah, so the claim is that this quantity, which is equal to this thing, is strictly less than 2. Right. So let's try to prove it by induction. Right. So base case is clear. Proof by, let's put a question mark over here, by induction on n. Always state your plan, right? So base case is n is equal to 1, right? So right, so the LHS is just square root 1 is equal to 1, and then that is less than 2. So that is fine, good. What happens in the proof of the inductive case, right? So induction hypothesis. Induction hypothesis is what? Square root of 1 times square root of 2 times square root of 3 times square root of n minus 1. Right, so you know what is happening, right? So induction hypothesis says this is less than 2. What do you do now? Right, so it's going the, so
I think we're providing an upper bound which is not a function of n would not be sufficient if you're using induction. So we would need an upper bound which is also a function of n.
Very good idea, right? So who is this? Abhinav? No, who was it?
So Aradhya.
Sorry?
Aradhya.
Sorry, I'm not able to hear. Could you just write your name on chat, maybe?
I'll raise my hand.
Acha, okay. Aradhya, okay, good. Yes, Aradhya, you are right. Maybe that is a good idea. So could you mute yourself now? Okay, so Aradhya's idea is the following. Aradhya's idea is, instead of having just this upper bound of 2 which you are trying to prove by induction, right? So this doesn't seem to go anywhere, right? So what his idea is, so his idea is that, okay, instead of 2, let us have some function of n as an upper bound. What function we will figure out, okay? And then it should be easy to prove that, okay, so this function should be such that it is easy to prove fn is less than 2 for all n, right? So this should be easy to prove. And now, so hopefully, using the structure, some kind of structure in this function f, you will prove that this weird square root expression is at most fn. That sounds like a plan. So Aradhya, what you could do is maybe try to figure out whether you can. Okay, so try to figure out such a function f. If you find a concrete proof, just post it on the discussion forum for all of us to see. What we are going to do right now is, on a high level, a similar idea, but we are not going to construct an f. Okay, so Aradhya, just give it a try, or other people can.
Okay.
Nishchay?
Sir, yes. So if we have to create a function, so sir, since both of the numbers in equality are positive, we can just raise the power by 2 to the power n on both sides.
No. That was not his idea. His idea was the following. So give explicitly state some function f with the following two properties. F of n is less than 2 to the f of n is less than 2 for all n. Right. So that should be the first property, which should be easy to verify, hopefully. And the second property, which you will try to prove by induction, is that this weird square root expression is less than fn.
So can we do like 2 to the power 1 minus 1 by n? Like, except for the base case, I think it will hold.
Then what is the use if the base case itself is not valid?
Just the equality. It will just give equality at base case. That's it.
Then that is fine. So you're trying to say that, okay, you will prove less than or equal to instead of less than.
2 to the power 1 minus 1 by n.
Sorry, what fn should I use?
2 to the power 1 minus 1 by n.
This one?
Yes, sir.
Okay. No, but why is it for n equal to 1? So this is 2 to the 0, which is 1, no? Where is the equality? That's
1
fine.
equal to 1 now.
So he's claiming the function that we have here and this fn, they are equal at n equal to 1.
Oh, that is fine. So yes, so you just want an inequality over here. So right? So fn strictly less than 2, if you can prove, then that is fine. If it's fine if this weird square root expression is less than or equal to fn, that's fine, right? You just need a strict inequality in one of the two places. That is good enough. Okay, so you sorry, who was this? I forgot the name. Samyak, did you tell this 2 to the 1 minus 1 over n?
Yes, sir.
Acha. Oh, 2 to the 1 minus 1 over n.
So like if you just replace all 2, 3 up till n by just 2, like it will be like this will be, oh no, sorry.
But then that's not legal, right? So this expression 1 to the 1 by 2 times 2 to the 1 by 4 times 3 to the 1 by 8 and so on. How is this as compared to 1 to the 1 by 2?
Decrease it.
Sorry?
Actually, I think he was trying to increase, but that will just decrease it. Like
exactly. So I'm not sure about this. So this fn equal to this doesn't seem to work.
So we can say that 3 to the power 1 by 8 is less than 2 to the power 1 by 4.
No, but you already have 2 to the power 1 by 4 over here, no?
No, sir, I'm using this 2 to the power n minus 1 till 2 to the power n. I'm substituting
So
those numbers.
are you saying ignore this 2 to the 1 by 2 and then you just 2 to the 1 by 4 is less than 2 to the 1 by 2, 3 to the 1 by 8 is less than 2 to the 1 by 4. Is this what you're trying to do?
Yes, sir. Suppose if you take 2 to the power 1 by 4, then I am converting 3 to the power 1 by 8 is less than 2 to the power 1 by 4. So I take them and I'll say that these product of these two is less than 2 to the power 1 by 4.
I understand what you're trying to say. Just get a concrete proof and put it on the discussion forum. We'll discuss it over there.
Sir, if we go by this, then we'll arrive at 5 raised to the power 1 by 32 is less than 2 raised to the power 1 by 16. But that's not the case.
2 to the 1 by 16. Very good. Good point.
But this is not true.
Yeah, this is not the case. Yeah, awesome. So I don't think this works. Doesn't seem to work. Okay. So in case you find some other function f, just write the concrete proof and post it on the discussion forum. Okay. Good. So instead of working with this product, we'll in fact work with this square root expression, right? And then, okay. But anyway, so even if you manage to get this proof, friends, please mute yourself if you're not speaking. Okay, so there are some raised hands. Abhinav?
Sir, we may use AMGM inequality here.
Okay, and then what?
Sir, so if we use AMGM, we'll get that this term is less than equal to 1 by 2 plus 2 by 4 plus 3 by 8 up to n by 2 to the power n.
What say that again? So the LHS is less than or equal to what?
1 by 2, rather less than 1 by 2 plus 2 by 4.
2 by 4 plus
3 by 8. 3 by 8.
Acha. So you're treating this as a weighted geometric mean and doing something about it.
Yes.
Is that so?
Yes.
Acha. So let's see. 3 by 8. 3 by 8 plus 4 by 16 and so on.
N by 2 to the power n.
Till n by 2 to the power n. True. And then what is this sum as n goes to infinity?
And if we calculate the sum, it is equal to 2 minus n by 2 to the power n.
2 minus n by 2 to the power n. Okay. So this is, okay, the claim is this is 2 minus n by 2 to the power n. Okay, maybe it is. I'll have to verify. So if you get, so basically what you're trying to say is your fn is this 2 minus n by 2 to the power n, and then maybe
then we don't need induction anyways.
Yeah, whatever. Use induction or use AMGM, whatever you have, that's fine. So just write out the proof. We are looking forward to seeing it on the discussion forum. Good. Any other questions? Srimanti, you had some question, I suppose.
No, sir. I wanted to say that if we we had done this before, suppose we increase, suppose we have suppose from 3 to 4 we all make it to 4, and then from 5 to 8 we make it all to 8, and then multiply. Okay. We could have a function of fn that way.
give it a try. Give it a try. If you have a concrete proof, post it.
Okay.
Okay. Sure. So what we are going to do is, on a high level, it's the same. You're kind of okay. So what is the problem over here? Why are you not able to prove this using induction hypothesis or rather principle of mathematical induction? The problem is, so you're trying to prove P of n minus 1 implies Pn, but then this P of n minus 1 is kind of too weak, right? So that itself is not good enough for proving Pn. Right, so you want to prove a claim of the form for all n Pn, right? So what you will do is the following. So you instead prove, right? Instead get some new predicate q. Okay, instead prove a claim of the form q of n implies P of n for all n. Right, so this is the first thing you will prove, and the second thing you will prove is using induction. You will prove Q of n for all n Qn. Right? So you are making a stronger inductive claim over here, and hopefully this stronger inductive claim is strong enough so that the induction goes through. So Q of n minus 1 implies Q of n. This kind of a induction step goes through, hopefully. And that is what some people are trying to suggest. So they are saying, okay, instead of proving this thing is less than 2, right? So your P of n is this claim, right? So this is P of n. Instead of what they are saying is, let's construct a new claim Q of n, which says that the left hand side is, I'm not repeating this left hand side. So L of LHS is less than some f of n, right? So this is the claim Qn, right? And then the two things you need to prove is Qn implies Pn, which means for which it is sufficient to prove Fn is less than 2 to the Fn is less than 2, and then you will prove this claim Qn using induction. So you will prove the fact that this weird left hand side is less than Fn using induction. Okay, good. So give it a try. High level idea. So we are, in the proof that I am going to present, so we are still using the same high level idea. Okay. So what we'll do is get a stronger claim. Right. So how do you get a stronger claim in this case? Right. So if you notice, if you just carefully observe this expression, right. So this expression essentially has some kind of a copy of itself embedded within itself. Abhinav, do you have a question? Your hand is up. Okay, apparently not. Okay. So I am referring to this specific copy, right? But the only problem is this copy doesn't start with a 1, it starts with a 2. Okay. So what we'll do is, right, so this doesn't seem to work. So let me get rid of this, or rather, doesn't seem to work. Right. So what I'm doing right now is just rough work that you will do, right? So on a scratch, on a rough paper, and then we'll construct the final proof by induction. Right. Good. So I want to kind of understand this copy. So what is the right level of abstraction for this copy, right? So what I'll try to understand is a more general expression of the form square root of m times m plus 1, or rather, how should I put it? Okay, let me put it in this way. Yeah. So, okay, let me put it this way. M plus 1 times square root of m plus 2 times square root of m plus 3 times blah 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 m plus n, right? Right, so there are number of nested square roots over here, right? So if we get, instead of this specific expression, if we get some upper bound on this for every m and every n, okay, so we can kind of substitute it over here and get something out of it. Okay, so now if you consider this kind of an expression, you can easily write some Python or whatever program and try to find what does this converge to. Okay, and then if you do that, you will realize that, okay, well, so this seems to be less than, this seems to be less than m plus 2. Right? So inspired from that, inspired from your whatever experiments you do, now you will make a stronger claim. Right? So stronger claim. Right? What is the stronger claim? For every m and n in what? Okay, so the domains are different. For every m in n union 0, right? So you finally need to plug in m equal to 0 in this expression, right? So for every m in n union 0 and for every n in the set of natural numbers, right? So this expression, square root of m plus 1 times square root of m plus 2 times square root of m plus n, right? So this quantity is less than m plus 2. And this is what we'll use, this is what we'll prove by induction on n. Right, so proof. Right, so observe that this claim implies this earlier claim. By the way, could somebody tell me whether they are able to see my mouse pointer? Right, so can you see where my mouse pointer is hovering on your screen?
No, sir.
Oh, that's the.
I think we can.
Okay, fine. So I'll take care of this. Yeah. So my point, the point that I was trying to make is that yeah. So this claim, if I just substitute in this claim, if I just substitute m equal to 0, I get this claim, right? So left hand side is same as left hand side, right hand side is same as right hand side, right? So in this sense, this is the stronger claim. Okay. There's something in chat apparently. Okay. Good. Fine. Right, so let's try to prove this stronger claim by induction. Proof by induction on n. Right, so what is the base case? Right, so what is the base case? N is equal to 1 because n is a natural number, right? So in the base case, what do you get? Square root of, you get on the left hand side, you get square root of m plus 1, right? That's it. Obviously, that is less than m plus 2, which is the RHS. Fine. So this base case is obvious. Induction hypothesis. What should be the induction hypothesis? Does somebody want to tell it? What should be the induction hypothesis? Right, we are inducting on m, right? Inducting on n, right? M has nothing to do with that. Yeah, somebody is saying something.
So for an integer is equals to n minus 1, this should hold. This condition holds.
So what should hold? So your induction hypothesis really is for every m in n union 0, right? For a specific n minus 1, this holds, no? So
yes,
for
sir.
every m in n union 0, right? Square root of m plus 1 times square root of whatever blah square root of m plus n minus 1
is less than m plus 2.
Is less than m plus 2. Right, so this is your induction hypothesis. Right, and so now what do you want to prove? So to prove, right, so to prove this claim, right, so rather, okay, so this is the induction hypothesis. This is what you will assume. Now what do you get on the left hand side? Left hand side is this weird square root expression, m plus 1 times square root m plus 2 times blah 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 square root m plus n, right? So you have lots of square roots closing over here, right? So this is less than, right? So this is left hand side. So now what is this less than? how are you using the induction hypothesis? Right, so here you have n nested square roots. Induction hypothesis tells us that if you have n minus 1 nested square roots, then things work out the way you want them to work out. Yeah, Rishabh?
So you use the hypothesis on m plus 1. So you
Exactly.
get it less than m plus 1 into m plus 3.
Good. Awesome. Very good, very good. So if you observe just this expression, right, excluding this outside square root sign, right, so that just contains n minus 1 nested square roots and it is of this form, except that your m is replaced by m plus 1 over here. That's all. Right, and remember your induction hypothesis holds for every m. Right, so therefore this is going to be less than, this is by induction hypothesis. Right, so this is going to be less than square root of m plus 1 times this entire expression. The induction hypothesis is it is less than m plus 3. Aradhya?
So I was able to find the bound on this product. What I did was, may I tell my approach?
Is it completely different from this? If it is, then I'll complete this proof and then I'll complete.
Yeah, okay, sure.
Good, right. So yeah, is this fine? Any questions on why I could replace this entire expression by m plus 3? Any questions about this? Any questions about this less than? Yeah.
Sir, we are applying induction on n, but why are we giving hypothesis on m?
Okay. Right. So this statement, the predicate that you are trying to prove involves two variables m and n. Right. You need to apply induction only on one of the two.
Yes, sir.
Right. So if you just imagine this 2D grid, right? So you are saying some statement about every integer point in this grid. Right?
Yes, sir.
So think of this as m, think of this as n. Right? So your induction hypothesis is telling you that okay, for this specific n minus 1, right? So everything is okay. So the claim is true for all the points on this line. And using that, you are trying to prove that the claim is true for all points on this line.
Sir, does this mean that in the last line we are assuming that the n is same, the constant we are assuming in the first statement?
No, I don't understand what you're trying to say.
Sir, like n is a fixed value or can it be variable?
It's for all m, no? It's so the claim is
not m, sir, n.
Acha. So n, so okay, so finally the claim is for all n something happens. Right, for this outside for all n, you are using induction. Right, so you are assuming that the inside claim for all m something happens, that kind of a claim is true for some specific n minus 1. And now you will prove that the inside claim is true for n also. Is that fine?
Sir, I mean that we are varying m but applying induction on n. That I'm not able to understand.
Acha. Okay. So let me just change the order of this. Let me slightly modify this. Okay. Right. So let me just, for all n in capital N, for all m in n union 0, something happens. Right. So now this whole thing. Right, so for all m something happens, right? So this is my q of n.
Yes, sir.
Okay, so now what is q of n minus 1?
Right? m plus 1 to m plus n minus 1.
Exactly. Right, so this is my q n minus 1. Is it clear now?
Yes, sir.
Awesome. Okay.
Good. Thank you.
Yeah. Okay, so now what? Now it's an easy step. Why can we say that this is less than m plus 2?
So because inner product is less than m plus 2 whole square.
Exactly, and that is by what inequality?
AMGM.
AMGM. Good.
So I mean, we don't even need to apply AMGM.
Okay, then what do you do? Actually,
We
you will
can
just
simply
I see.
expand
You'll
it.
just square it and whatever, cancel out terms and get something.
Yes, sir. I will square both sides and I'll
M
show
plus
that 1 is greater than 0.
I see. Yeah, I get your idea. Yeah, possible. So yeah, either use AMGM or just square both sides. Or square both sides. Right, so here you will get m squared plus 4m plus 3 on the left hand side, and on the right hand side you will get m squared plus 4m plus 4. Yeah, you're right.
So we
Okay,
can take
good. So
we can take
Yeah.
m plus 2 as x, and it will become x square minus 1, which is less than x square.
Fine. Makes sense. Makes sense. Good. Fine. Awesome. Right. So this finishes the proof.
Sir, but we are still left with one crucial step here. No? We have
What step?
assumed that our induction hypothesis holds for all m, but we have not
Correct.
proved it yet. Means we have to apply one induction on m also.
Yes, sir. That's what I was saying.
Well, wait. What is the base case? What was our base case? Right. So our base case was, right. So for n equal to 1, so our base case was for all m. Okay, maybe I didn't make it clear. The base case that we are trying to prove is, the base case itself is for all m square root of m plus 1 is less than m plus 2. That is the claim in the base case we are trying to prove.
Yes, so what I am saying is, sir, I get it that for the base case m plus 1, it would be under root of this would be less than m plus 2. This is true for all m. But here in the LHS, in the induction, when we proved induction hypothesis, we used that the same thing holds for m plus 1. But we cannot really say that it for sure. No?
I don't understand. So
that
again,
is
so
what
your Qn, look. So syntactically, your Qn itself involves for all m within it, right? So as I said earlier, your Qn claim, or rather Q5 claim will talk something about all points on the 5th horizontal line. It will talk about all points on a single line. Right, you will use that fact to prove the claim on all points in the line above it.
Yes, sir. What I am saying is, sir, we don't know that our Q5 claim can cover all points. So because our claim could be something covering like a triangle in this region.
Well, no, that's not the way I have defined, right? My Q0 claim, I have defined it to be the claim on all these points. Q1, yes, I am saying that it's the claim on this point. What is the definition of Qn?
I still don't get it, sir, because in the induction hypothesis, we have assumed that this would be true for all m, but we have never proved it. Means, in fact, I think we should use induction on m once. Because, sir, even if you are, sir, what I am saying, sir,
look, in the base case itself, there is that quantifier exists, no?
Yes,
in
sir,
the base case itself, you're saying for all m something happens.
Yes, sir. So listen, sir, if we have a region of A by B, let's suppose a rectangle A by B in which we have to prove that our claim Q holds. Okay, sir. For the base, suppose on one base we have the claim true for a complete base, but our claim could be something like which holds for a particular triangle including the base. So it would not be true for all the bases at a certain height. What I'm saying is this.
Okay, so let me restate what I understood of what you are saying. So you are saying that okay, your claim is true only in this triangle. Suppose, is that what you are saying?
This could happen. Yes, sir, this could happen. That's what I'm saying.
So then your proof is going. If that is the case, if the claim is true over here and false over here, your proof is going to fail somewhere. If you try to give this kind of a proof.
Yes, sir, but we have assumed that our claim is true. So what I'm saying that, but we have on doing this, we have assumed that if it is true for y equal to 0 up to x equal to b, then it would be true for y equal to 5 and x equal to b. But that does not holds here. That's what I'm saying.
No, but that's what I'm saying. So the induction hypothesis is not telling you that the claim holds for these 5 points. The induction hypothesis is telling you that the claim holds for all points on this line.
No, so basically,
I'll ask in discussion forum.
Okay, sounds good. Sounds good. Yeah, that's better, I think. Yeah.
Sir, I think I understood what he is meaning to say, sir. He is saying that suppose the baseline is Qn minus 1 of this triangle, and then you have using that you have proved that above that line we have proved for one case of n, Qn, comma a special case of m, but we have not proved that for all the other points on this line.
Acha. Okay. So yeah, the answer to that is this is not any specific m, right? So whatever I am saying over here, right? So yeah, so for any m, the following. That's all I'm saying.
Okay, sir.
Yeah. Okay. Fine. So let's take this.
I got it.
Yeah. Okay. Any other question? I think there was a pending question from Aradhya, or rather suggestion. Aradhya, what is it?
So I managed to find I managed to prove the existence of an upper bound for this product. So what I did was that I took the logarithm with respect to base e of both sides.
Okay.
So this gets converted into half into 1 plus 1 by 4 into 2 plus 1 by 8 and so sorry into log 1 and log 2 and so on.
Good,
so
okay.
what I did was I used the fact that log n by n limit n tends to infinity is equal to 0. So
I see. Put this up on the discussion forum. That might be a promising idea. We'll discuss it over the discussion forum. Is that fine?
Yeah. Okay, sir.
Yeah, that looks like a good, reasonable idea to me. Fine. Okay. So any more questions about this? Any more questions about this? Right. So yeah, if there are more serious questions, we can do it definitely in the, let's say even in the tutorial session. That's fine with me. Okay. I mean, the high level point I'm trying to drive over here is if you if you can't do an easy task, try to do a harder task, right? Sometimes that is manageable. Okay, using whatever set of tools you have. Okay, good. Awesome.
Is this quantity of any specific interest like this limit? Is this value known or like?
I don't know. I just thought it's a cool application of the idea that okay, you actually prove a stronger claim than what you are required to prove.
Okay.
Okay. Cool. So let's get rid of this. Okay. So now what we are going to see is another avatar of the same principle of mathematical induction, but it's not immediately or probably for some of you it's not immediately possible to recognize that it's essentially the same avatar of the same or rather the another avatar of the same person. Okay. So it is what is called the well ordering principle, right? So what is the well ordering principle? Right. So if I write down the statement, you'll say, okay, what the hell? This is so trivial. Okay. So well ordering principle says if S is any non-empty subset of the set of natural numbers, then S contains a smallest number. Let me explain. That is a number that is smaller than all other numbers in S. Looks trivial, right? Every non-empty subset of natural numbers contains the smallest number, right? Something that is less than everything else in that set. Fine. But just note that if I were to replace n by the set of integers, suddenly this statement is not true. If I were to replace n by the set of rational numbers, again this statement is not true. even if I were to replace the statement by the set of positive rational numbers or non-negative rational numbers, still it is not true. It is very specific to the set of natural numbers. Okay, and I'm saying that this is another avatar of the principle of mathematical induction is the following, right? So, well, the principle of mathematical induction as well as this statement kind of look equally trivial, right? But when you try to develop this theory of numbers using a bare minimum set of axioms, right? So you need to take one of these statements as an axiom, and then you can take the other statement as a proof. If you assume, if you take the principle of mathematical induction as an axiom, then you can prove the well ordering principle. Or if you take the well ordering principle as an axiom, you can prove the principle of mathematical induction. Okay, so I'll put this up as a tutorial problem for you to kind of try out. Okay, assuming principle of mathematical induction, prove the well ordering principle, and assuming well ordering principle, prove the principle of mathematical induction. Essentially, they are the same. Usually every proof that you can use, you can write using principle of mathematical induction can also be written using well ordering principle, except that it might start to look complicated and ugly and not so intuitive. But you can do that, and vice versa. Right, but our aim for this course is to write proofs that are extremely intuitive and obvious looking, right? So which is why this is another tool that could be helpful for us. Okay, so let us see this tool in action. Right, so the comment that I wanted to make is not valid, not true, if we replace n by z or q or q greater than or equal to 0 or even r or whatever you like in the above statement. Right, so I hope people see counter examples. Right, so raise your hand if you cannot see a counter example which kind of from which you can infer that the statement is not true if you replace n by q. Or in other words, raise your hand if you cannot construct a set of rational numbers which does not have a smallest element. Okay, let's say even non-negative rational numbers. Okay, Aryan, good. Right. So Aryan, look at this set of numbers. Q is the set of 1 over n such that, or rather, I am not talking about Q. Sorry. Look at this S. S is the set of 1 over n such that n is a natural number. Right. So this is a subset of rational numbers. Right. This is non-empty, right? Because why 1 is in this set? But what is the smallest element in this set? Right, so this does not have a smallest element.
So,
yeah.
So is it that we are saying that the smallest element is kind of not defined or something? Because
it's not even defined. Yes, exactly. So for no matter what element you pick from this set, you can always find another element which is less than that and also in the set. Right?
Yes, sir. Yes, sir. So
yeah.
Now I got it.
That's the point. So this very special property of subsets of natural numbers, and it does not hold for all these. If you replace the set of natural numbers by integers or rationals or non-negative rationals, nothing. Real numbers, nothing. Okay, so this does not have.
What about 1 by n square?
What about what? Yeah.
What if we change the function?
This one?
Yes, sir.
Same argument. What is the smallest element in this set? Is there a smallest element? Right? If you pick 1 by 100 squared, well, you'll find 1 by 101 squared, which is less than that.
Okay, sir.
Right? So that's the point. Aniruddha?
Won't this depend on how you define smallest number? Because any countable set and
it's with respect to the usual order on the set of whatever.
Okay, but if you go ahead and take the rationals and you say that 0 is the smallest rational, and then you kind of make a 1-1 mapping from the rationals to the naturals and then define a order on that, then it
so
will
you're
follow.
so you're changing the order now. So you're changing the order. So all I'm okay. So you're going into more abstract orders in some sense. All I'm talking about is the same, is the very basic order on whatever all these numbers which we have studied in school so far. Okay, so if you redefine, then that set might become well ordered so far. Yeah, so if you define the order, if you kind of define an appropriate order on the set of integers or even the set of rational numbers or whatever, you might be able to convert it into a set which is well ordered. But with respect to the standard order, it's not a well ordered. So these are not well ordered sets. Shibashish?
I was also having a similar question. Like, does it depend that how we define the set? Then it may have a smallest element or not for these cases also.
Yeah, obviously. So if you just take a singleton set, obviously that has the smallest element. There is unique element, right? Or even a finite set. Well, yes, right. But the claim is but the well ordering says if S is any non-empty subset, or rather, in other words, it's saying every non-empty subset of N has a smallest element. Right, so as soon as if you replace N by, let's say, Q, and then you actually construct one set which does not have a smallest element, that is good enough to say that, okay, the well ordering principle does not apply to the set of rationals. Okay, Isha?
So can you give an example for all integers? So a set which is not well ordered.
Just take all the negative integers.
Okay.
Yeah, Divyanshu?
So like someone mentioned that we could define an order by mapping the rational numbers to the natural numbers. So in that case, would this argument would this set S have a smallest element in that case?
We are going to see this in maybe about a month or so. But for a short answer, yes. If you, instead of the usual less than relation, if you kind of completely redefine it in some weird way, it is possible. We'll see it in another month or so.
Like it may be possible, but is it possible in this S also, which we have just defined over here?
Yeah, exactly.
Yeah, okay.
Right. You can define some weird order on the set of rational numbers so that every non-empty set is actually going to have a smallest element. We are going to see such examples.
Okay.
Yeah.
Sir, excuse me. Sir, this 1-1 mapping would also only be true if the set is countable. Infinite or countable.
Yeah. So you're running ahead. You're right, but you're running ahead. We are going to look at countable sets and so on. You are right. Yes. Okay, but let's just focus on the well ordering principle with respect to the usual order and only on the set of on subsets of natural numbers. And right now, let us try to see how you can prove things using this well ordering principle. Okay. Good. So. Okay, so now let us try to solve this problem. Okay, so consider the following equation, right? So I'm sure you must have studied how to solve linear equations, quadratic equations, cubic equations. Do you know how to solve cubic equations? I mean, are you aware of just like there is a quadratic formula? Are you aware of a cubic formula?
Sir, I know there exists a cubic formula.
One at a time, please. I cannot hear anybody. Just cannot hear anybody. Please raise your hands. Yeah, Arin?
Sir, I know there exists a cubic formula, but I don't remember.
Okay, fine. Vivanshu? Okay, Siddhant?
So we hit at one solution by trial and error.
One at a time. Siddhant.
So we try to find one solution by trial and error, and then the quadratic which is left out of it is found out by quadratic.
But I don't want a trial and error solutions. Just like you have this quadratic formula minus b plus or minus blah 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 blah. I want a cubic formula. Is that
I've heard of one called Ferrari's formula, but I don't know what it is exactly.
Fine. So there is a formula to solve cubic equations. There is a formula to solve degree 4 polynomial equations with one variable. But beyond 5 and so on, there does not exist a formula. So it involves some heavy duty math. So let's not get into it. What we are trying to solve is the following equation, right? So the equation we are trying to solve involves in fact 3 variables, not just one. And the equation is the problem is the following: find all solutions, find all integer solutions. I'm not looking for real or complex solutions. Solutions of the equation x cube plus 3y cube plus 9z cube is equal to 0. Okay, what is an obvious solution of this equation?
0, 0, 0.
0, 0, 0.
Good.
0, 0,
good.
0.
Awesome. Good. 0, 0, 0 is a solution. Anything else? Anything else? I mean, you don't have to give the solution. Even if you kind of give ideas, okay, the solution must look like this and so on. All those are acceptable. Fine.
You set one of them 0 and the sum of the other two are 0.
Do you get a solution out of this?
You will not.
Not possible.
Yeah, it's not possible.
Not possible. Okay, fine. Dhruv?
Yes, sir. I was going to say that it is not possible.
Oh, you think 0, 0, 0 is the only solution?
Yes, sir.
Yes.
Why, Dhruv? Why do you think so?
So because we can take modulo 3
okay,
and find that x is divisible by 3.
Very good.
So
Okay.
x is of the form 3x1. Then we divide.
Let me write down. You're right on the right track, but let me just write down whatever you're saying. So just give me some time. So so if x, y, z is a solution, then 3 divides x, right? So what do you get? So for x is equal to some 3 times x prime for some x prime in z. Now what?
So can you rewrite the equation in terms of x prime?
Good. So you will get 27 x prime cube plus 3y cube plus 9z cube is equal to 0.
So now we can divide it by 3.
Cancel out a 3. Very good. Okay, 1 sec. So there's something on chat. Okay, fine. So divide by 3. So therefore, then this implies 9x prime cubed plus y cubed plus 3z cube is equal to 0. Okay.
So now if we will continue in this manner, then we will get that y is also divisible by 3. Then we will get z is also divisible by 3. Then we will get x prime is also divisible by 3. So at stage we will have to assume that x is of the form 3 to the power k, but then we will find that 3 divides it again, and we assume that it has a highest power of 3. So that is the contradiction, and
you have the very good, you have the right idea. It's just a matter that it slightly needs to be more formal. Okay, and we'll try to make it. Yes. Ramanuj?
Yes, sir. So for this, we can do it similar to how we did it for root 2 is irrational. So we take x, y, and z such that x, y, and z have at least one of those numbers is doesn't have a factor of 3 or something like that, because we can factor out 3 and it will still satisfy, because you can, for example, if you have some arbitrary x, y, and z and you take 3 out of 3 to the power k out of them.
So you are saying if x, y, z is a solution, then 3x, 3y, 3z is also a solution.
So basically,
is that what you're saying?
We can find by the well ordering.
We can take x, y, and z such that x, y, and z you can take 3 common out of them, so that X, Y, and Z, at least one of them doesn't have a factor of
Exactly. I agree with you. So essentially, I'm just rephrasing whatever you're trying to say. So you're saying that if X, Y, Z is a solution, then 3x, 3y, 3z is also a solution, and that's the correct statement. Is also a solution. Or and conversely, or rather what you're trying to say is XYZ is a solution if and only if 3x, 3y, 3z is also a solution.
Like basically, so we can start with XYZ to be co-prime, right? Or if they are not,
exactly. So if you make this statement, then you can say that, okay, well, so since this is true, there exists a solution where x, y, z are co-prime. If there is some solution other than 0, 0, 0, there exists a solution in which x, y, z are co-primes. You could try to make these kind of statements.
So I think we are implicitly using the well ordering principle. So in order to
formalize that's what I'm coming to.
So in order to formalize it, I think we should define K as the highest power of 3 in the GCD of XYZ, and this maps it. This maps the triplet XYZ to natural numbers, and now we can apply the well ordering principle.
Maybe that is one way. If you can construct a function to just put it on discussion forum.
Sir, the last implication implies that y, z, and x prime is also a solution. Like
here what we have proved over here. Yes, you are right. Yeah.
Yes, sir. So we'll write y, z, and x prime is also a solution. But as x prime is x by 3, so like eventually we are decreasing the solution set. Like the triplets, we are decreasing the triplets by 3.
Intuition is right. Intuition is bang on. Yeah, spot on. Just
so eventually we'll reach a minimum element.
Exactly.
By well ordering principle.
Intuition is absolutely spot on, except that you missed a little detail that, okay, I'm asking for integer solutions, right? So you should not be saying the solution decreases. You should say the solution moves closer to 0, if at all.
Yes, sir.
Right? Yeah. Parth? Oh no, that was by mistake, I think. Okay, fine. So let's try to write a clean solution, extremely clean solution by using the well ordering principle. Okay. Right. So this argument is correct, and that is what we'll use in the proof also. So claim no other solution. No solution. Okay. The only solution to the equation is 0, 0, 0. Okay, proof. Right. So now you want to use well ordering principle, and for that you need to construct some kind of a set, non-empty set of integers. Non-empty set of natural numbers, and then you say that, okay, it has the smallest element, and using that smallest element somehow you arrive at a contradiction. Okay. So let me just write down the proof for now, and then we'll go back and see in the details of the intuition of that proof. Okay. So proof. Consider the set. Okay, so what set should I use? S is equal to, let's say, I hope this works, 2 times the absolute value of x plus 3 times the absolute value of y plus 4 times the absolute value of z, such that x, y, z is a solution of the equation, which means x, y, z is in z cross z cross z, and x cubed plus 3y cubed plus 9z cubed is equal to 0. Okay, and okay, sorry, I should also mention, and xyz is not equal to 0, 0, 0. Yeah, so by the way, the people who are giving solutions using GCD and so on, you will have to separately take care of cases where some subset of xyz is 0. Right, so all those cases you'll have to worry about, but yes, that's a promising approach. Okay, fine. So this is some weird set which I have defined, but this set is going to be useful for us to prove that there is no other solution, right? So okay, proof by contradiction. So assume, okay, so proof by contradiction. Okay. Assume the equation. Aradhya, what is it? Or rather, let me just finish the statement and then I'll come to you. Assume the equation as somebody is not muted. I'm getting noise. Let me mute you all. Okay, good. Thanks. Okay. Assume the equation has a non-zero solution. Okay, so then what does that imply? Then S is not empty, right? And moreover, right? So absolute value of X, absolute value of Y, absolute value of Z, all these are integers. In fact, they are non-negative integers. So this is going to be a subset of natural numbers, right? So not all three are zero. So this is going to be strictly positive, right? So moreover, S is a subset of L, right? So by well ordering principle, right? By well ordering principle, S contains a smallest element. Say call that element K. Right. So now why is K in the set S? So since K is in the set S, so then what happens? So there exists a solution X, Y, Z such that, right? So there must be somebody who is responsible for bringing K into the set S. Who is responsible? Suppose some solution X, Y, Z is responsible, right? So then what do you have? So then you must have K is equal to 2 times X plus 2 times absolute value of X plus 3 times absolute value of Y plus 4 times absolute value of Z. Okay. So now good. So now let's leave this for a while, and then now let us apply this argument. If X, Y, Z is the solution, then 3 divides X. X is equal to 3 X prime for some X prime in Z, and all these things happen, right? Right. So let us just copy this argument. So since X, Y, Z is a solution, since X, Y, Z is a solution, 3 divides X, X is equal to 3 X prime. All this happens. So therefore, this happens. Ooh, this is a problem. Right. So therefore, this happens. And now let me get rid of all this and create some more space on the slide. Okay. Good. So now what? So 27x prime cube plus 3y cube plus 9z cubed is equal to 0. So therefore, cancelling a 3, 9x prime cubed plus y cubed plus 3z cubed is equal to 0. Right. So therefore, y, z, x prime is also a solution. Right. So now if yz x prime is a solution, let's get back to the definition of S. Right. So therefore what? 2 times absolute value of y plus 3 times absolute value of z plus 4 times absolute value of x prime right? So this is an element of S by definition of S. However, what? So 2 absolute value of y plus 3 absolute value of z plus 4 absolute value of x prime is nothing but what? 2 absolute value of y plus 3 absolute value of z plus 4 by 3 times absolute value of x, and 4 by 3 is less than 2, so this is less than 2 times absolute value of x. 2y is less than 3y, 3z is less than 4z, right? And oops, sorry, this should be a plus, right? And this is precisely equal to k. But what did we assume? We assumed that k is the smallest element of S, right? So this is a contradiction to the minimality of k, right? So what does this essentially mean? This S is a subset of integers which does not have a smallest element, and that is a contradiction, right? Sachit?
Sir, the inequality it should be like for if x is 0.
Sorry?
Then, like in case x is 0, like you can't say it is strictly greater than this.
In case x is 0, you're talking about this inequality?
Yes, sir.
No, but even if, okay, we know that at least one of them is not 0, no?
The last inequality.
Yeah, in that case, we have to do for y and z.
Sorry, Sachit, what is it?
Like, sir, I'm saying that it only for x it's not sufficient because in case x is 0 in the last inequality.
So you're talking about this inequality, right, or no?
Yes, sir.
Yeah.
Like if x is 0, then we also have to prove this for y and z also, no? Like
you don't need to, that's what I'm saying. You don't need to look. So we know that at least one of them is not 0. Right? And then these coefficients, so 2y is strictly less than 3y if y is not 0. 3z is strictly less than 4z if z is not 0.
Okay.
Right? So one of them, yeah, so at least for one of them, x, y, and z, you are going to have a strict inequality. So this is what z, no? Right? So therefore, this is a contradiction to the minimality of k. Okay, any questions? We have just 1 minute left. Aryan?
So I was saying that why you came up with the 2x plus 3y plus 4z, that's clear. But
that's
how
clear?
you
okay,
came,
good.
but how you came up with
How do I
that?
come up with? How do I come up with? So it's a slight amount of trial and error. What I did was, let us just try some number of the form a times x plus b times y plus c times z, and then for the proof to work, what do we need? So for this inequality to work, you need that what? You need a less than b so that you can replace a times y by b times y. You need b less than c so that you can replace b times z by c times z over here, right? So a times y by b times y, b times z by c times z, and similarly you want that c by 3, or rather c by 3 is less than a, or in other words c is less than 3a, right? So if you take any, and you want a, b, and c to be integers, right? So if you take any 3 integers a, b, c such that this is true, the proof is going to work. Divyanshu?
So like, can we define an ordering on like x, y, z from like n into n into n and then do something like this? Like, is it possible?
That is also possible. That is also possible. So you will have to define an appropriate ordering. With respect to that ordering, you will have to show that the n cross n set is well ordered. That will need a proof. Right? So the well ordering principle only talks about the set of integers. It doesn't talk about the set of n cross n and so on. Right? So you will have to prove that, okay, with respect to this ordering that you have constructed, the set is well ordered, and then you can go with the rest of the argument. That is possible. Okay, all right. So if any one last quick question, because we are already out of time. Okay, good. So if there are no questions, yeah, that is the end of class. So see you on Thursday. Chalo, bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.